Okay, so welcome all. Welcome back to this second lecture of the event. The title of the lecture is Models of Non-Classical Set Theories, and his speaker is Dr. Sourav Tarafder. Dr. Tarafder is an assistant professor at St. Xavier's College, Kolkata. He was awarded PhD in the year 2017 from the Department of Pure Mathematics, University of Cambridge, under the supervision of Professor Mihir Kumar Chakraborty and Professor Benedict Loy. He was a visiting researcher in the Department of Philosophy and Human Sciences, University of Campinas, Sao Paulo, Brazil, during the period October 2019 to October 2020. His research interest is in the area of classical and non-classical logics, non-classical set theories. So I would like to invite Professor Dr. Sourav to please start the talk.
Thank you, Professor Akhil. Thank you for inviting me from the Association for Logic of India to deliver my lecture, deliver this presentation in the occasion of the World Logic Day. So as we can see, the title of the presentation is the Models of Non-Classical Set Theories. Like is understood that actually we are going to talk about different kind of models of different kind of set theories. Okay, and in my lecture, I will just explain that which kind of set theories actually we will like to talk about and which kind of models actually we are going to introduce. Okay, so if we just go ahead, the outline of my talk will be like this. The first, we are going to see that what the constructions of the Boolean valued models of ZFC. Look, here when we are talking about the models, like I will be like throughout my lecture, I will stick to this kind of models which are called the algebra valued models of set theories. Okay, so but before going to explain the general kind of results, we have to first understand which was the first Boolean valued models of the classical set theory. So I will start my lecture with this thing, and then we'll go to the next point, which will be the generalization of these Boolean valued models of the classical set theory. And these generalized algebra valued models things actually this kind of works I did in my PhD, as Professor Akhil had said already, that under Professor Mihir Kumar Chakraborty and Professor Benedict Loy, and I'll spend some time to explain that how this Boolean valued models construction can be generalized as a generalized algebra valued model thing. Then next, we will discuss this thing like non-classical algebra models of some fragments of ZF, which will be there in the second point even. And then a non-classical algebra models of the full ZF. And when I'll discuss this thing like non-classical algebra models of the full ZF, actually these are works of Professor Giorgio Venturi and his PhD student Santiago Djokovic, who both of them are here already in this meeting. I'll explain their results. And then next, we'll go to this point where I'll explain. Okay, look, like, well, so before going to this point, like, as I want to just mention here, that, well, so suppose we have this kind of models, then what are the next demand from the mathematical perspectives from these kind of models? Like, of course, we have models of set theories like classical or non-classical. And then, of course, the next mathematical demand will be that which kind of mathematics we can produce inside these kind of models. So the next point will be on the foundation of mathematics in a class of non-classical algebra models. Of course, like I'll take some subclasses of those kind of non-classical set theories, and then I'll try to show some results which will actually show some foundation of mathematics inside those non-classical models. And next, we'll just see that the last point of this lecture will be on the discussion of some independence set theoretic results in some non-classical set theories. Well, so this area is new, like because we already know that independence set theoretic results are a very deep branch or very important branch of classical set theory. But of course, it's true that in non-classical set theories, this branch is not much explored yet. So in my visit in Brazil, uh, like, in that 1 year, like we did some research on these independent set theoretic results on non-classical set theories with Professor Giorgio Venturi and together with Santiago Jokovic. So I will show the results, that which kind of results we have found, and the lecture will end with that. Well, so let's go to the first point on the constructions of the Boolean valued models of ZFC, which was done in 1964 by Peter Vopenka and Sourav, and which was built to explain Cohen's forcing in a equivalent way. And what was the construction? Let's see that. For seeing that construction, first, what we have to start with, like, we have to first start with a complete Boolean algebra B. Well, so I know that there are many participants. Some of my students are also participating in this lecture and who doesn't have much idea about some notions here, but I will try to explain the things so that it is at least the overview is understood. So let's start with the complete Boolean algebra B, any complete Boolean algebra B. Then what we do? Then for any ordinal alpha, we just define a collection of functions like this, V alpha B. What is that? It's like that V alpha B contains functions where the range of the functions is the subset of the Boolean algebra B here, the base set. And then what are the domain of these functions? X. The domain of the functions contains again some functions which are built in the previous steps. That means, suppose we are trying to understand what is V10B. This B is the Boolean algebra we have started with, and suppose we want to understand what is V10B. What is V10B? V10B contains some functions where the domain of all these functions are some functions which are built in the previous steps, like V0B, V1B, V2B, like that till V9B. And what are the range of this function? The range is just a subset of the Boolean algebra we have started with. Okay. Then we make all these kind of collections V alpha B, and we change this ordinal number alpha one by one and ultimately find these kind of collections. Finally, what we do, we take the union of all these collections and we get this collection, this class VB, where we have just written that this VB contains all those functions X, where this X is some of this is inside of some of this V alpha B, which we have built like this. That means, what is VB? Like, what are the elements of VB? Simply, the elements of the VB are some functions, right? Where the domain of the functions are again functions. But you take any functions from here, what is its range? Its range is a subset of this Boolean algebra. That means, like, the functions and the images of the functions are lying in the Boolean algebra we have started with. Okay, so this collection will be called VB. Well, then what do? We extend the language of the set theory ZFC by adding constant symbols corresponding to every element of VB. Okay, so we have made VB like that, and then after making this VB, what we do, we add constant symbols for every element of this VB in the language of GFC. Okay, and in this way, we extend this language. After extending this language, what we do, we just assign a map this from the collection of all the sentences of this extended language we have just made here, from that to the elements of the Boolean algebra we have just taken. How we are just doing it? Well, so we first define this function over the atomic formulas in this language, atomic sentences in this language. How we do that? You know that we take any two elements u and v in VB, and we know that corresponding to u and v, there are constant symbols already added in the language. Suppose we are writing the constant symbols corresponding to u by u for the simplicity, and the constant symbols for v by v itself. Then u belongs to v is a sentence. It's an atomic formula as well. And the value of this sentence under this function is given by this. This is, look, when we are defining belongingness, the value of u belongs to v, we have just used here equality, the value of x equal to u in this case. And when we are defining equality, the assignment, this function over u equal to v, we actually use the belongingness here as well. Okay, so that means this is a like recursive definition. Like for defining belongingness, we are using equality, which are already like defined in the previous steps. And for the equality, like we are using belongingness, which are actually defined in the previous steps. So recursively, ultimately, we are defining belongingness and equality like this. Okay, by the way, like for the participants who are actually seeing these things for the first time, there are many, I know, as I've said, that some of my students are also attending this. Like for you, just to tell that, okay, so this is like very complicated kind of algebraic notions, right? So it is not important to understand that how this thing is defined, but just to understand that, I'm just explaining it here, just to understand that you take some sentences, you take this assignment function, and this assignment function take this sentence to some value of the Boolean algebra B you have started with, right? So that means u belongs to v is some Boolean value under this function. U equal to v is some Boolean value under this function. How we are getting these Boolean values? The algebraic expressions are written here. Okay. Well, so whenever the atomic sentences are defined like that, then we just extend this assignment function homomorphically like this. Like we know that whenever we are taking two sentences sigma and tau, then this sentence sigma meet tau, its value under this assignment function will be the value of sigma meet the value of the sentence tau in the Boolean algebra. All the things are defined like this. Okay. Here you see that the negation of a sentence, its value will be defined as the complement of the Boolean value here of sigma. Okay. Now see these two things. What is the value of these like quantified formulas? Like for all x phi x here, its value will be the value of phi x, where x, you just take the meet of all the value of phi x, where x is belonging to VB. Okay, so that means you take every element from VB, you plug it here, and then you find its value, and ultimately you take the meet of all those values. The value ultimately you get will be the value of this form sentence for all x phi x under this assignment function. Similarly, what will be the value of there exists x phi x is this. It's the same thing you do, and then you take the join of that thing, and ultimately you find this value in the Boolean algebra. Okay. Now, next.
Can I ask a small question?
Yeah.
Uh, so the VB is like a hierarchy of sets, like the functions are the like truth values of sets, like if something is in the set or not, like some kind of that.
Are you talking about VB? Like
Yes,
this
yes.
one?
Like this VB looks like a hierarchy, like
Yes, of course. Like
okay.
it's defined in the cumulative hierarchies way. Okay. So this contains elements which are functions. Okay. But then this assignment function, this one actually is giving the truth value, what you have just said, to the sentences of the language of the set theory. Okay. This assignment function actually is giving the truth value to the sentences because they are actually giving some value in the Boolean algebra we have started with, right? And ultimately what we are doing, we are taking the sentences of this extended language and then we are assigning some Boolean value to that sentence through this assignment map. So actually this
So
assignment map is giving truth value to the sentences.
so are the functions in VB sort of extensions of the idea of sets, like classical sets, like that?
Yeah, actually we are going to do that. Like, yes, like that will be an algebra valued model finally. So though it contains all the
Okay.
functions, but ultimately we are going to see that that collection will be algebra valued models of some set theories. Okay, we'll see that. That's the whole point here.
Okay.
Okay, and immediately you see point number 7 and you will get your answer. What we're saying that a sentence sigma will be called valid in VB, or VB will be called a model of a sentence sigma if the value of sigma under that assignment function, that will be a Boolean value, is equal to 1. What is 1 here? 1 is the top element of the complete Boolean algebra we started with, right? In that case, it will be denoted as VB double turnstile sigma. Understood? So here you see that one more time, I'm just uh, uh, trying to explain point number 7 and giving some time on this construction, because like ultimately depending on these kind of constructions, the entire lecture um, uh, will go or will pass through.
Sir,
So one more time, I'm just telling it here that we are taking a sentence sigma and then we are saying that this sentence is valid in VB, or VB is an algebra valued model of the sentence sigma if the value of this sentence under this assignment function is getting the value 1, and we will denote it as VB double turnstile sigma. Okay, there was another question, I think.
hello.
Yes.
Sir, can you go back to the previous page? Yeah, previous to that, huh?
This one.
No, previous to this. Yeah.
Yeah. Okay.
Yeah, here. So the left hand side is an element of the Boolean algebra, and the right hand side the assignment of x equal to you also in Boolean algebra, and Vx is so x is in the Boolean algebra and V is the function, so that is why Vx is in the range and that is also in the Boolean algebra. That is why it is defined, right?
Uh, no, like your idea is correct that since Vx is a Boolean algebra, that's why we can make this Vx meet x equal to u, which is also Boolean algebra. This is meaningful. And since this is meaningful, we have defined the value u belongs to V with this expression. You're right that if Vx would not be a Boolean algebra, there would be no meaning of this thing at all, right?
Yeah, yeah.
Yes, of course it's true, but it's
Thanks.
not the case that what you are saying, that to explain or to express it like that, we had to make the range of V as a subset of Boolean algebra. It's the other way around, right? So we have defined it like that. And then since it is that, this has some mathematical meaning. And ultimately, this whole thing is giving a Boolean value. Understood?
Yeah, it makes the assignment map defined. Yeah.
Yes. Okay. Well, once we have defined it like that, and then this is the celebrated result, what I just told, that for any complete Boolean algebra B, this VB, we can prove that this VB will make all the axioms of ZFC valid. That means that you take all the axioms of ZFC, like the extensionality, pairing, everything, whatever you want to take it, that is a sentence, and try to find what is the value assigned to that sentence through that assignment function. You will get the value of that any axiom you take from ZFC under that assignment function as 1. And by this definition here, that if the value is 1, then we'll say that VB makes that sentence valid, or VB becomes a algebra valued model to that sentence. We can write that, look, for all the axioms of ZFC, VB becomes an algebra valued model. Okay, and then V becomes a model of all the consequences of all those axioms. Okay. Next, you see that now if we just replace the complete Boolean algebra by complete hating algebra, okay, and then we do all the similar kind of constructions, right? So here, instead of taking the Boolean algebra, we are taking the hating algebras. We do all the similar kind of constructions, and then in probably 1978, Grayson first showed that this thing becomes an algebra valued model of intuitionistic Zermelo-Fraenkel set theory. So this is the classical Zermelo-Fraenkel set theory, and then we can prove that if B is replaced by this hating algebra, then this thing will be an algebra valued model of the Zermelo-Fraenkel axiom system, where the base logic is the intuitionistic logic. Okay. Now the immediate question comes from here, that why only hating algebra? Like, what happens if we change the construction of the Boolean valued models? We change the complete Boolean algebra B by some other non-classical algebras. Then what happens? Of course, okay. So before going to that, like, we have to just so we have to discuss this point first, that what will you mean by these generalized algebra valued constructions? For this slide is dedicated for that. Like, we are going to just explain that what we will mean by the generalized algebra valued models, and then we'll go to that study, that if we change the Boolean algebra by some other non-classical algebras, not only hating algebras, then actually what happens. So to define these things generally, what we are just doing here, consider some algebra A where this thing is a complete distributive lattice. Okay. And then we define a subset D of this A as a designated set, which is just a filter. And what is a filter? We all know that, like, D will be called a filter if all these three conditions holds, right? That 1 belongs to D, 0 doesn't belong to D, and then it is closed under if if A is in D, then and B is above A, then B will be in D. And also, like, if you take any two elements A and B from the designated set, their meet will also be in the designated set. Like, if in this set, if this actually holds, then we say that this set D is a filter, and any filter will be called a designated set here. Then similarly, you construct VA. Look, now our algebra could be anything. It could be a Boolean algebra, it could be a hating algebra, it could be something else, with these two operations involved, like the implication star with the meet and join. And then you make the similar kind of constructions, VA, right? Like VB we made before. And then you define an assignment function, this, or denoted by this, similarly from the collection of all sentences of the extended language into this algebra A. So again, like, you are defining by this assignment function, like, it's a like this assignment function actually giving the truth values to the sentences of the extended language here. Okay, but note that one thing, that here we are saying that define an assignment function. This assignment function could be defined like in any way. We are not saying that this assignment function has to define in only the way which was defined in the Boolean case, Boolean valued case. It could be like that, it could be something else. But in general, we are just saying that you just take an assignment function from the collection of all sentences of the extended language to A, fix a designated set D of A, and then this actually holds. Like this is taken as the definition that a sentence phi of the extended language is said to be valid in VA, denoted by this, with this designated set D here, or simply by this, if we know from the context which is the designated set, if the value of this sentence phi we have taken under this assignment function we started with, okay, is inside this set D. See carefully here, like what I want to just mention, that is this something that when we define the Boolean valued models or hating valued models, did we do something else? Actually not. Why? Because in those cases, this D was only the singleton set 1. You see, what was the definition when we said the Boolean value, when we explained the Boolean valued models? Here we said that a sentence sigma will be called valid in VB if the value of the sigma under this assignment function is 1, right? Only the value is 1. That means if in this case you take a Boolean algebra and you take a designated set as only singleton 1, then saying this and saying this are actually equivalent, right? So actually we are not, like in the Boolean valued case or hating valued case, we did not do anything else. Actually, we did this thing, but now we have just generalized the idea of these algebra valued models by introducing this designated set as a filter, any filter, not only singleton 1. Okay. Well, so as if this designated set contains all the truth values by getting which will say a sentence is true. It's like that. Its interpretation is like this, that you start with some sentence phi, and if its value under this assignment function, some way we have defined, if its value under this assignment function is in D, then we'll say that phi is true. It's like that. Okay.
Can I ask a question?
Yes, sir, please.
Is there a possibility that there can be more than one designated set?
In this study, we did not explore that.
Okay. Okay.
Actually, what happens, like when we talk about the logic of the algebra with the designated set, actually we take one algebra and fix a designated set on that algebra, and then we talk about the logic of that algebra. And since here we have to take the logic of those algebra in our account when we will study the set theories, actually we do not go for more than one designated sets.
Yes.
We fix a designated set when we are taking an algebra.
Okay.
The entire study is like that.
Okay.
Okay.
Thank you.
Well, next, before going to see that how much generalized results we can get, let me just introduce one very important property here, which is called the bounded quantification property, which says this, that suppose we take an algebra here like this, where this one is a complete distributive lattice, and you take a formula phi x here, okay, with one free variable x here, and we say that bounded quantification property of phi holds in VA if for any u in this class VA, this property actually holds. See, what is so special of this property? if you can remember that whenever we have defined this assignment function over for all x, okay, we did this actually. Look, whenever we define for all x, phi x, we took the meet over all the elements of VB. Okay, this meet is over all the elements of VB, but here we are making this for all x, but this meet is not over all the elements of VB. Okay, in the left hand side, it is the meet is over all the elements of VB. In the right hand side, it is not. So it might happen in some cases, these two things are actually equal, and in some cases, these two things may not be equal, right? Now, let me tell you that as we have just said here, that if for some phi x and for any u, this thing holds, then we'll say that bounded quantification property holds for this formula phi, right? Let me just inform you that for the Boolean valued case or the Hating valued models, actually this holds for any formula phi. Okay, but this might be changed for if you consider this algebra to be something which is not a Boolean algebra or a Hating algebra. There are many examples. We found that there are algebras A for which, and there are formulas phi for which this property actually do not hold. Okay, well, so what is so important with this property? We'll see in the next slides. Next, we are going to, as we have just said, that what happens if the Boolean algebra is replaced by some other generalized algebra? Can we get some reasonable amount of set theory in that model? That means what we are saying, that can we make a reasonable amount of ZF axioms true? That means a reasonable fragment of ZF true in an algebra valued model, VA. In the top of V, we are writing A here. And this, like, which kind of properties of this A has to be there so that this VA makes a model of some reasonable amount of set theory. We are now coming up with some properties of this algebra A by which we can get an algebra valued model of a reasonable fragment of CF. What are the properties? The properties looks very simple like this. Like if all these three things holds, we'll say that an algebra this is a reasonable implication algebra. In addition to that, if this property also holds, we'll say that this algebra is a deductive reasonable implication algebra. Okay. Just I want to draw your attention in P1, like here you can see that if this implies is replaced by if and only if, like implies and implied by, then this property, the resultant property will make the algebra an Hating algebra, right? You don't need all the other three. All the other three things can be derived if we just change this implies by implies and implied by. It will make this algebra a Hating algebra. That actually is the definition of the implication in the Hating algebra, right? But in all these four properties, we are not taking implies and implied by, but only this side of the implication and the other three properties. If this holds, then we'll say that this algebra A is a deductive reasonable implication algebra. Then what next? That means what is like our aim, or like you can already guess that we are just what we are going to do. We are just defining some kind of algebras, and ultimately we are going to say that, look, if you take this algebra and you make the algebra valued model VA like the Boolean valued models, then these algebra valued models will make a reasonable fragment of the set theory valid, right? Now, which kind of reasonable fragment or which fragment, whether it is reasonable or not, it's up to you, but which kind of fragment we are actually going to make. For understand that which kind of fragment we are going to talk about, we need this definition of the negation-free fragment. Here it is written formally, but I'm just trying to explain in simple words by what we mean by the negation-free fragment. It's very simple, like you take the language and you take the collection of all formulas where negation is not present in any of the sub-formulas. I repeat one more time, like you take the collection of all the formulas. Which kind of formulas? You take a formula and you see that formula and there is no negation involved in the entire expression of the formula. So it's kind of that it's negation free, the formula is, and the whole collection like that is called a negation free fragment. Okay, and any formula from that negation free fragment will be called a negation free formula. Okay, well, then we have this result which we were talking about, which we were aiming for from the beginning, that what happens if the Boolean algebra is replaced by some non-classical or some generalized algebra. You take a deductive reasonable implication algebra A, and then you make VA. If we can prove that the bounded quantification property holds for all negation-free formula phi, that means, one more time, let's go to the bounded quantification property. Well, come here. You see that the bounded quantification property was this, right? And we are saying that what is NFF BQ phi? It means that, like, if your phi is negation free, then this thing holds for all negation free formula phi. If that holds, then we say that NFF BQ phi holds. That means negation free, like BQ phi holds for all negation free formula phi. Okay. So let's go to the statement of the theorem one more time. We are saying that if A is deductive reasonable implication algebra such that NFF bounded quantification property holds, then we can prove that all these axioms, extensionality, pairing, infinity, union, power set of ZF, and then these instances of the axioms, NFF separation and NFF replacement. What is the meaning of NFF separation and NFF replacement? Like, we know that whenever we write the axiom separation, there are some formulas involved, right? We will take the instances of those axioms where the formulas are negation free, and those instances will be called NFF separation. Similarly, the instances will be called NFF replacement. So we can prove that all these axioms and the instances of the separation axiom and replacement axiom, which are the NFF separation and NFF replacement, all are valid in VA for any designated set D you consider from A. That means, irrespective of which designated set you are considering from the algebra, this actually holds. Okay. By the way, just one more thing. Let me just draw your attention one more time here. Look very carefully that we know that in classical logic or in the intuitionistic logic, we can write negation in terms of implication and another one more symbol bottom here, right? Like, we can write negation phi as phi implication bottom. So that means that all the formulas of the classical set theory or the intuitionistic set theory can be replaced by some formula, or any formula will be equivalent to some formula which is negation free, right? If we consider bottom in our language. Okay. And that means by this theorem, we can say that, look, what is NFF separation then? NFF separation is just the separation, because, like, the negation can be replaced by, negation phi can be replaced by phi arrow bottom, this thing, like where negation is not involved. That means negation phi can be replaced by some formula which is negation free. So that means NFF separation, NFF replacement will actually be separation and replacement in the case of classical set theory or intuitionistic set theory. That means that this actually generalizes the theorems when we say that Boolean valued mod like VB, where B is a Boolean algebra, makes all the ZF axiom true, or VH, where H is a Hating algebra, makes all the intuitionistic all the axioms of IZF true. Actually, this as a corollary gives those two results as well, right? Why? Because any Boolean algebra and any Hating algebras are deductive reasonable implication algebra, as I have said before. And BQ phi holds for all phi. And as I've said that NFF separation and NFF replacement are just the separation and replacement in the classical and the intuitionistic cases if you introduce bottom in your language. Therefore, we can say that, look, as a corollary of this theorem, both the theorems that VB makes ZF valid when B is a Boolean algebra, or VH makes IZF valid when H is a Hating algebra, these two results become corollary of this theorem. Okay. Well, now the point is that, can we come up with some example of like non-classical, like some algebras which are not Boolean or Hating, which actually gives this kind of like, which actually which becomes deductive reasonable implication algebra and make this NFBQ phi true, so that we can just get all these axioms like this valid in that algebra valued model. Can we come up with some algebra which are not Boolean or intuitionistic? Yes,
Sourav,
we can. Here,
can I ask a question?
yes, yes.
Yeah. Okay. So, yeah. So we were constructing these different structures,
Yes.
and then showing that they validate ZF or ZFC, right?
Yeah.
What
Yeah.
about, are there the other way? I mean, like, can I ask questions like, if these class of structures, these models do validate these different axioms, then they must have a Hating algebra or Boolean algebra embedded in it. I mean, like, which are the necessary conditions? I mean, do they ensure ZF axioms,
Yeah.
or
Yeah,
a bit
actually,
unfair to ask?
yeah. No. But it's a good question. But I can say that actually we'll show you that there are non-classical algebras in this lecture, even like, which was a research work of Giorgio Venturi and Santiago, who actually came up with some algebras which are non-classical, neither neither it's the Boolean algebra or the Hating algebra, but they are making all the ZF actions true.
Ah, okay. Okay, that answers me then.
Yes.
Okay.
So we'll see this construction.
Yeah, thank you.
Yeah. So let's come back to this point where, as I've said, that like, start with this three-valued algebra PS3, where these operations are defined like that, and then you fix the designated set as 1.5, right? So this is actually a lattice which is a linear lattice, like a three-valued lattice. 1 is the top, half is in the middle, and 0 is in the bottom. Okay, three-valued linear lattice here. And then you take the filter, which is half and 1, right? So you forget about 0 and you take half and 1 there. And then what happens? We can prove that this PS3 actually is a deductive reasonable implication algebra. Not only that, NFA BQ phi holds in VPS3. And we know that if these two things holds, like, you see the theorem one more time, like, if some algebra is a deductive reasonable implication algebra and NFF BQ phi holds, then all these axioms are valid, right? In VA. That means we can say that, look, you take PS3 and then you take, and we can prove that these are deductive reasonable implication algebra. Not only that, NFF BQ phi holds in VPS3. And that means that all these axioms and the instances of separation and replacement with the negation-free fragment are valid in VPS3. In addition, we can prove NFF foundation in VPS3 separately. Okay, And that means ultimately we can get this theorem that VPS3 makes NFF-ZF valid. Okay, NFF-ZF means that the negation-free fragment of ZF. Well, but then what? Like, is this algebra PS3 with that designated set? Is it like our known like classical or intuitionistic? It's giving our known classical or intuitionistic logic? Actually not. We have this theorem, like this algebra with the designated set is actually a maximal paraconsistent logic. What is that? Like, we'll say a logic paraconsistent if this holds. Like what? Like if you have two formulas phi and psi in your language, so that psi cannot be derived from phi and negation phi, which is always true in classical logic, right? That any formula psi can be derived from phi and negation phi for any formula phi, right? But if it fails, then the logic will be called a paraconsistent logic. Okay. And then what is the meaning of maximal? Look, why I am explaining this maximal here, because I will need one of these properties later on. What is the maximal here? Like here we can prove that the logic of this algebra with this designated set is a proper fragment of classical propositional logic. Okay, it's a paraconsistent logic, but it's a proper fragment of the classical propositional logic. In which sense it is maximal? In this sense that you take a theorem of classical propositional logic, which is not a theorem of this logic, okay, and you add that theorem as an axiom of this logic. The resultant logic will ultimately be equivalent to CPL, the classical propositional logic. In that sense, it is maximal. Like you just add one theorem from outside, like it's a it's a fragment, proper fragment of classical one, right? So classical one is a bigger, and inside it, the logic of PS3 is there. And then you take something in between, and which is a theorem of CPL, and you just add that thing in the smaller one as an axiom, and ultimately the smaller one becomes the whole set, which is the classical propositional logic. Okay, in that sense, it is maximal. What we'll need later, that the logic of PS3 is a proper fragment of the classical logic CPL, that we'll use later. Okay. Okay. Next. So that means what actually we get? We got that VPS3 was making NFF-ZF valid, and ultimately we got that PS3 gives rise to a logic which is paraconsistent. So ultimately, combining these two things, we can say that, look, VPS3 is an algebra valued model of some paraconsistent set theory, right? So that means, look, this is something like which is neither like classical set theory nor an intuitionistic set theory, but something else. And we are getting some algebra valued model of that. Okay, following the constructions of the Boolean valued models. Well, now extensions of PS3, as Jam was asking, that we are just reaching to that goal. Now, see here that we'll say that a linear ordered implicative, like an algebra as a linear ordered implicative algebra, if these conditions hold. What are the conditions? Like this structure will be a bounded lattice having top and bottom elements as 1 and 0. Okay, so we have this algebra, and then this is a bounded lattice having top and bottom elements as 1 and 0. Then the lattice order is a linear order. This was expected, right, from the name itself, that we have this lattice and the lattice order will be linear. That means like PS3. That's why we have just said this is an extension of PS3. PS3 was 3 value, 1, half, and 0, right? Now what we're doing, like you take an entire linear thing, like it might be finite, it might be infinite, it might be anything, like you know. Okay, that is a lattice, but you make this lattice a bounded lattice. Okay, as we have just said here. And then how we are going to define this implication? Look, what ultimately we are going to get? We are going to get some implication which satisfy all the properties of the reasonable implication, right? You define the implication like this, simply. What is a, like, if you just see the implication of PS3, what actually happens? You see that actually this holds there. Like if your A is non-zero and your B is 0, then this implication gives you the value 0. Otherwise, every implication gives you the value 1. Okay. So if you define your implication like that for any two element A and B in A, and if in addition it satisfies these two conditions as well, then we'll say that this lattice a linear ordered implicative algebra. Well, now Venturi and Djokovic proved that this linear algebra A is actually deductive reasonable implication algebra. Not only that, it satisfies NFF BQ phi as well. And we wanted only these two conditions, right, to make NFF, the negation free fragment of ZF, valid in this algebra model. That's why we can say this, right? For any linear ordered implicative algebra A and any designated set D, this actually make NFF ZF valid. Okay. So now we talked about PS3 3-valued thing. Now it's not 3-valued, but you take any linear thing. Okay. And similarly, we can prove that that algebra valued model actually makes the negation free fragment of ZF valid, like the VPS3. Yeah. Is there any question from someone? Okay. If not, let's go ahead. Okay. So till that we have understood. Now what we are going to do, we know that look, in PS3, in that 3-valued thing, we had a operator star as well, right? Which was the algebraic interpretation of the negation of the language of set theory. What we are going to do here is that now in this linear implicative algebra, we are going to introduce that kind of unary operator star. How? One way is this. We are taking an unary operator star 1, which says this. Simply what it actually, we have now the linear order lattice. We have a top element 1, we have a bottom element 0. So the star of 1 goes to 0, the star of 0 goes to 1, and the star of anything in between is itself. The same thing happened in PS3. You remember? In PS3, what was the complementation operator? Like 1 goes to 0, 0 goes to 1, and the negation of half was half itself, right? The same kind of negation we are taking here, okay, with the linear kind of thing. And then what happens, like we can prove that now you take a linear thing, you introduce a complementation operator like that, and now if you take a designated set which is not only the top element, but something like from some point, the upper part, right? The way we have defined the designated set. If it is like that, then the logic of this structure is paraconsistent. Like PS3, you remember PS3? What was our designated set? Half and 1, right? It was not only singleton 1. So something from in between, and then it's the upper segment, upper part of that linear thing. Okay, if you do the same kind of thing here, you can prove that this structure becomes a paraconsistent, the logic of this structure is a paraconsistent logic. And of course, that this becomes an algebra valued model of a paraconsistent set theory, which validate NFF-ZF. Of course, right? Why? Because already you have seen that VA itself validates the negation free fragment of ZF. You are introducing this star. So that means we can say that this becomes an algebra valued model of a paraconsistent set theory, which validates at least the negation free fragment ZF. Because already VA was satisfying NFF-ZF, right? For the linear implicative algebras. Okay. Now let's define another star like that. So what is this? Like we are defining another complementation operator as this. Like you are taking the linear implicative algebra 1, like it's saying that you are taking 0, the bottom element, its negation is the top element, and anything in between, its negation is 0. Okay, if we define another complementation like that, then what we get? We get the answer what Ramanujam asked some time ago. Look, Venturi, Djokovic and Venturi proved that for any linear ordered implicative algebra A associated with a unary operator this, defined like this. This one makes all the ZF axioms valid. Okay. Now I'll give few few time here. Like if someone wants to ask some question on this, like you may ask. As Jordan Santiago is also here, like if I am unable to answer, probably they'll be able to answer.
What about ZFC? I mean,
no, well, so wait for that C. So
okay,
we'll say something later on in this lecture. At least for this thing, like we are not saying anything about C. At least for this.
And what are the
may I ask one question?
Yeah, please.
Does this result, I mean this theorem,
yes,
does it mean, say without C, does it mean that this V to the power A, this model A star 2, right? This model,
yes,
and the Boolean valued model,
yes,
they are almost the same or similar.
Well, so actually I was expecting this question, and that's why I gave a few minutes here, like to think. Actually, what happens? The answer depends on the designated set D. The point is that if you are taking a linear algebra and your designated set D is the ultra filter, like D contains everything other than 0. So from the above 0, you are taking anything in D. Okay? If your this designated set is the ultra filter, then this linear algebra with this D becomes its logic becomes classical. But if the designated set D is not the whole ultra filter, then it's not. Why? Because it's simply, we can see this result because for this fact, like you take some D, like which like outside D there are some element other than 0. Okay, suppose it is like this, then you can see that actually modus ponens fails there. Why? Because you take something inside D, suppose A, and you take something outside D, suppose B. Okay, then what is A implies B? The way we have defined the implication, A implies B actually is 1, right? So that means A was inside D, and A implies B, which is 1, is also inside D, right? So that means both A and A implies B are inside D. But from that, we cannot derive B because we took B outside of the designated set. But then, of course, probably you are thinking that if modus ponens fail, how it is making full ZF valid? Here, there is an assumption here. Look, by ZF here, we are meaning all the axioms, the non-logical axioms of ZF, not the classical logic axioms. All the non-logical axioms, like the exponentiality pairing, only you take these axioms and you take those sentences and try to find the values under that assignment function of that sentences. All the values will be actually 1. And that's why it's making full, like all the axioms of CF, the Zermelo-Frankel axioms only valid in this model. Is it clear? Like, am I clear?
So it really gives the insight that ZF and the logic, underlying logic,
yes,
they are essentially different.
Exactly. The underlying logic is actually different. If you take
You can go on taking the underlying logic in many different ways.
Right.
Always taking these proper actions.
Right.
ZF set there. Right?
Right.
Is it okay? Yeah.
Yes, exactly. Yes, it's true. Like depending on D, the the logic of this algebra with D will be different, and which will definitely not be classical, neither be it's neither be classical nor be intuitionistic, and that means it is something, some other non-classical logics, right? And actually it is giving a non-classical set theory where all the axioms of ZF are true.
Yeah.
Yeah, and this result is published,
So,
as I said,
so
that
by classical, when we talk about classical set theory,
yes,
it means ZF plus the classical logic.
yes, yes, true. But here, as I've just said, that here by saying ZF in this theorem, only in this theorem, whenever we are talking about this ZF, we are actually meaning the axioms of Zermelo-Fraenkel only.
I understand that. That's
Yeah.
correct. Yeah.
Yeah, but like yeah, so I could use a different symbol here, but I thought that I'll tell it in the presentation. That's why I did not use some different symbol. But all the ZF axioms are valid here. Okay.
Okay.
Okay. Well, so now, as I have just said, that we will see that after finding all these kind of models, like which kind of mathematics we can see inside these models. So to get that, what we'll do, like now what we have the linear implicative algebras, and then we are making the algebra models on those kind of algebras. But now we will not take the full class of that, but we are making some reduction here, that we are not taking all the linear implicative algebras, but a proper fragment of that. By what? Like I'm just saying that which algebra now we are aiming for to get foundation of mathematics inside the algebra valued models. We are taking this kind of algebras now. Like we'll say some algebra is well-ordered deductive. If you just take the linear deductive algebras where the lattice order is not linear but well-ordered, that's all. So in the previous case, it was the linear ordered thing. Now you are taking only the well-ordered thing, the lattice order. Okay. And then we say that this is a well-ordered, and we can like we can understand that this is a deductive reasonable implication algebra, though. So the subcollection will also be a deductive reasonable implication algebra here. And then what we do, like the implication is defined similarly, the way we defined it in the linear one. Okay. Next, from that, now on these well-ordered deductive reasonable implication algebra, we are introducing a negation. Which kind of negation we are introducing? You see, the negation, the property of the negation, we have just taken only this, that the top element goes to 0 and the bottom element goes to 1. That's all. We are not saying anything in between. So now, so what we have a well-ordered algebra, and then like the top element is going to 0 and the 0 is going to the top. Yeah, so yes, so and then we will say that these algebras as the PS algebras. See here again, like since we are not giving any condition on the negation of the elements which are in between 1 and 0, so depending on the negation of the elements which are in between, the logic of these algebras could be changed. And of course, you see that suppose you are taking only a well-ordered algebra like a PS algebra which contains only 2 elements, 1 and 0, and by the definition, it is just a two element Boolean algebra, right? So that means these PS algebras like contains classical like the Boolean algebras as well. Okay, and like if there are more than 2 elements, it will contain some non-classical algebras as well. So as we have just said here, that depending on the star and the designated set actually we are talking about, these algebras will provide different kind of non-classical logics which are paraconsistent, paracomplete. What is paracomplete? I did not give the definition here. We know that a logic is paracomplete if there are formulas phi such that phi join negation phi is not true, right? So these logics of these algebras could be paraconsistent, paracomplete, neither paraconsistent nor paracomplete as well. Okay, but of course those algebras are also like the directly reasonable implication algebras and NFA-BQ holds because they are the subclass of the linear algebras, which was the collection of algebras of Giorgio and Santiago, and that's why those algebra of course will validate NFFZF, right? So that means that this VA will make some non-classical set theory, actually will be an algebra model of some non-classical set theory or classical set theory depending on the algebra and the discriminant set. Okay, now we are interested on this kind of algebra valued models. Okay, inside these algebra valued models actually we can prove these things. This is the first order formula corresponding to the mathematical induction, where this is the first order formula stating that X is the set of all natural numbers, and here this is the first order formula stating that Y is inductive. And then we know that if X is a set of all natural numbers, Y is a subset of X, which is inductive, then X is equal to Y, right? This is a mathematical induction, and then we can prove this thing. That you take any PS algebra A and you take any designated set of that algebra, then in that algebra valued model, MI is valid. Well, what next? Now, here comes to the second question of Ramanujam. What about the action of choice? Like, the action of choice is the first order formula written here, right? So I'm not going to say this thing because it's a very big first order formula. Like its length is very big, as we all know that this is a first order formula stating f is function. This is a first order formula stating that the domain of f is u. This is a first order formula stating that z is a pair of xy. And then this whole thing, whole formula will be the action of choice, the first order representation of action of choice. And then we can prove this thing as well. That look, here the first time we are stating something of the ground model V here. We are saying that if V is something where action of choice holds, which was the ground model, right? We took some V and over this V, we made these algebra valued models, right? So if in this V, action of choice holds, then for any PS algebra A with the designated set D, in VA, action of choice also holds. Okay, so now it is not only NFFZF together with the action of choice. Okay. Look, well, so look here that there is a negation involved in this first order formulation. That's why I have just written it. There is a negation involved. Still, we can prove this AC in this VA. So this is not only the model of NFFZF, but some other axiom of ZF containing negation as well. Okay, so we can prove it. Then we can prove these two theorems, which are very demanding theorems of cardinal numbers in mathematics, Schroeder-Bernstein theorem and Cantor's theorem, in all these PS algebra valued model for any designated set D. Both holds in the algebra valued model VA for any PS algebra A, and you take any designates. It doesn't matter whether it is the ultra filter or like some filter other than the ultra filter. Well, so both these things hold. And then here comes the much more deeper result. We can prove this thing, that if you have a PS algebra A and a designated set D, and you start with the ground model V of ZFC, okay? Now you can prove this. If like GCH is valid in V, if and only if GCH is valid in this algebra valued model. So this is much deeper result here. Like as I've just said, that means the general continuum hypothesis is valid in the algebra valued model if and only if it is valid in the ground model, actually. If your algebra A is any PS algebra and you consider any designated set, doesn't matter. This will hold. Well, so once we have all these results, now I think that, well, so which I did not note here down, that actually this is not all for the foundation, like all the basic cardinal arithmetic, like the addition of the arithmetic, multiplication, exponentiation, all these things actually hold in these PS algebra valued models. Like the properties of the addition, multiplication, and the exponentiation, which we get in the classical mathematics of cardinalities, all those properties hold in these PS algebra valued models. Okay, I did not note it down. As for the time, like we have to pass on to the next thing, which is another direction of these algebra valued models, which, as I said, that was missing in the non-classical set theories. And as I said, that when I was in Brazil, like Giorgio, me, and Santiago wanted to explore the things on this branch, and few convincing results we have found. Now we are I'm just going to show those things. What are these? First of all, like, what is the definition of that some formula phi is independent from a theory T, where both the theory T, the formulas in T, and this formula are written in the language of ZFC. We know this thing, right? That will say that phi is independent from T if there exist two models, M1 and M2 of T, where in one phi holds and in another phi doesn't hold. I'll just give a few seconds here, pause here. If you have any question, you can ask on this slide. Well, so actually,
Sourav,
yes.
So it's not on this slide, but the previous ones.
Okay.
We talked about the GCH and actually cardinal arithmetic and all that being derivable.
Yeah.
So are you saying still that classical logic does not play any role there? You are still just taking, as you explained a little while ago, simply the ZF axioms, the proper axioms, and like you're adding these things, right? Is that still the case?
Yes. What I'm saying, that GCH has a first order formulation, right?
Right.
And that formula is valid, like that. That's all. Like the value under that assignment function of that formula is in D. That's all I'm saying. Only this. And now, if you just say that all the equalities of that algebraic calculations, if that take place in the meta language or in the meta mathematics, that is something else. Like, I'm not going to that portion, but like simply if you just calculate algebraically that what is the value of GCH, of course, like it's actually the proof of that thing is not actually like that. It's much more complicated than that. But actually the meaning is this, that if you can calculate the value of this first order sentence of GCH, then ultimately that value will be inside D. That's all.
Okay.
And if it is inside D, then you can prove actually that in V, GCH holds.
Okay, thanks.
Yeah. Okay. Yeah. So here, what I wanted to, to draw some attention of you is that, look, in the third condition, generally in classical case, what we do, we write that, like sometimes we write that like M2 is a model of negation phi. Of course, in classical case, this expression and that expression are equivalent, right? That when we say that phi is independent of T, and we just replace this 3 by M2 validate negation phi, that expression and the expression written here are equivalent in classical case. But actually they are not equivalent in whenever you are considering this non-classical set theories. And we had to take this definition over that one, which we generally use in the classical case, because for some reason, like due to the time, I'm not going to explain what is the exact reason, but yeah, these results are already yeah. So when they are in a paper of me and Giorgio, like when that will be published, like you can see the restrictions for which we could not take that formulation or that expression in that paper. Well, but let's take this thing as a definition of the independence of this formula phi from the theory T, and then let's go ahead with that definition. And then let's take this. Suppose phi is independent from ZF. Okay, here, just a second. Like now onwards, whenever I will say ZF, actually I am talking about ZF with its classical logic axioms. Okay. Again, I could use some different symbol here, but to keep things simple, I just written ZF. Here, whenever we'll just talk about ZF, now onwards, we are just actually saying ZF with its classical logic fragment as base axioms. Okay. So if a formula phi is independent from ZF, then phi is independent from any fragment T of ZF, right? That is true. That is of course true. We know that. Like if from ZF we cannot prove or disprove phi, then from a smaller theory we cannot prove or disprove phi. But then this question is valid. Like if I say that how to prove this thing, how to prove this one, then the proof is very simple, right? That phi is independent from ZF. That means ZF has two models, M1 and M2, which satisfy phi, and another one doesn't satisfy phi, right? And since T is a fragment of ZF, then to prove that phi is independent from T, we just consider those two models, M1 and M2, which were the model of ZF, right? And we can say that, look, those models are the models of T as well, because T is a fragment. And those two models, one satisfy phi, another one doesn't satisfy phi, right? And that's why phi is independent of T. But we can ask this question, that can we find two models, M1 and M2, of this fragment, which are not models of ZF, the bigger one, the bigger fragment, such that one makes phi valid, another one doesn't make phi valid? Then what will be the answer? Right? Now, I'm not taking two models of the bigger theory. I'm trying to get two models of the smaller fragment, which are not the model of the bigger theory, which one makes phi true, another one makes phi false. Does there exist two models like that? Okay. The answer is yes, with these conditions. Like, let me just quickly go through the conditions. Like they're big. Let me just explain it simply. Like it's saying that suppose you have a sentence phi and a proper fragment T of ZF, and you have a algebra A. What happens? Such that phi is independent with respect to ZF, and the logic A is a proper fragment of the classical propositional logic. Okay, and VA becomes a algebra valued model of phi and T both. If this happens, then we can say that, look, there are two algebra valued models of T, but not of ZF, which do not agree on the validity of phi. That means one makes phi valid, another one makes phi invalid, if all these three conditions holds. Okay. Okay. And what is an application here? Like, to go to the application of this theorem, like, just let me define something here. Like, we did not say anything about this cross product thing here in this presentation, because again it will take a long explanations, and only the thing I want to mention here, that whenever we'll talk about A cross B, the product of two algebras, like two complete distributive lattices, we are actually like the operators of these things are defined coordinate wise. That's all. So you just take it like that, and then we can prove that this product is again another complete distributive lattices, which has many properties like shared by the component thing. Okay. And then we are now taking this definition. What we are saying that suppose A is a complete algebra, okay? Then by A ZF, by A dash ZF, we mean a fragment of ZF, which is valid in all algebra valued models of the form this, where A is fixed, but B is any complete Boolean algebra. So that means you take a complete Boolean algebra B, you make A cross B, you make this B A cross B, this model, and see which formulas are valid here, which sentences. Now you change your B, and then you make the same thing and see which sentences are valid there. And you take all these collections, take the intersection, and that intersection becomes AZF. That means AZF contains all those sentences which are true in this algebra valued model for any complete Boolean algebra B. That's the definition, okay? If this is the definition I've taken, then we can prove that, look, if this A now can be replaced by PS3, PS3 was that 3-valued linear algebra, right? 1, half, and 0. So you replace A by that 3-valued linear algebra, PS3, and you can make that PS3ZF. By this, we can prove that NFFZF is included in PS3ZF. PS3ZF is a proper fragment of ZF, and PS3ZF is a paraconsistent set theory. That means there are set theoretic sentences having those paraconsistent properties. Okay? Then this thing we can prove using the theorem we have just shown, that there are two algebra valued models of PS3ZF, which is a proper fragment of ZF. There are two algebra valued models of this proper fragment of ZF, which do not agree on the validity of the continuum hypothesis. That's showing the independence of the continuum hypothesis from PS3ZF. Look, those two algebra valued models are not the model of ZF. That means what actually we are getting? We know that continuum hypothesis is independent from ZF, right? That means since PS3ZF is a fragment of ZF, continuum hypothesis will be independent from PS3ZF as well. But this theorem says something more. It is saying that, look, not only that, PS3ZF has two different models which are not models of ZF, where one makes continuum hypothesis valid, another one makes it false. If we go ahead with that, like now what we did, we showed this thing, like we had the bigger theory, and then if something was independent from the bigger theory, then it is independent in the smaller theory, but something more we have said. Now we are saying something else. Is it possible that we have a bigger theory, ZF, and something which is not independent from ZF, but it is independent from the smaller theory, proper fragment? Yes. We have proved this theorem in that regard, which says, suppose A is a complete algebra and phi is a sentence of the language of ZFC, such that one of these two things hold. Okay, that means VA becomes an algebra valued model of this formula, and negation phi holds in ZF, or VA is not a model of phi, but phi holds in ZF. If any one of these two things hold, which are exclusive properties, then we can say that this formula is independent from the proper fragment, but not from the bigger theory. We'll see some example like this. Consider this formula. See here, this is an instance of the separation axiom where negation is involved. So that means this is an instance of the separation axiom which is not NFF separation, right? Like which is not negation free, because in this instance negation is involved. Take this instance of the separation axiom, and then we can prove, look, since this is an instance of the separation axiom, what happens? This is true in ZF, this is valid, and we can prove that in VPS3 this actually false. This instance of the separation axiom which involves negation actually falls in VPS3. So that means from this one, what we can say, look, in VPS3 that instance is false, and this is true in ZF. So what we can say, that this instance of the separation axiom is independent in this proper fragment of ZF, which is PH3ZF, but not from ZF. Why? Because we know that this is an instance of separation axiom, that means it is valid in ZF, but this is independent in this proper fragment. One more example, and we'll finish my lecture by this slide. This example is also very interesting, which says that consider a three-valued heating algebra H3. So what will be VH3? VH3 is a model of the intuitionistic Zermelo-Fraenkel set theory, right? So you take the heating algebra H3, and suppose phi is a sentence which intuitively says this, that kappa is the cardinal number of a set, then 2 to the power kappa is the cardinal number of its power set. Suppose this sentence is first order formulation is the formula phi. Okay, we know that this thing right, you see there that it is well known that in IZF the cardinality of the power set of a singleton set cannot be 2. We all know that, right? Because we know that if it is included this property that the power set of a singleton set, if the cardinality becomes 2, then that actually is equivalent to law of excluded middle. Okay, so in IZF this is not true, right? That means in IZF phi in general is not true, but phi like that's why in VH3 phi is not true, but this is true in ZF, right? This is true in ZF. That means H3ZF, which is a proper fragment of ZF, here this sentence is independent, but it is not independent in the mother theory, which is the bigger theory, which is ZF. Okay, so one more time to explain this thing, that this sentence is independent, that the power set, the cardinality of a power set is 2 to the power the cardinality of that set. This sentence is independent of this fragment of ZF, which is H3ZF. But of course, we know that that is true in ZF. That's why it is not independent.
Sourav, how are you defining double turn style here?
Like from which, sir? Like ZF double turn style 5?
Here or there? I mean, when
Like,
not, yeah, these two cases.
No, so this one is like the value of phi under that assignment function is outside D.
No, that means with respect to a designated.
Right. Here we are taking, yes, we are taking H3 with the designated set only singleton one, like the heating algebra, simply.
Okay.
And all these independent results, you can find here, like in this paper. Well, so thank you very much.
Yeah, so we can have some questions, comments. So if anyone would like to ask, please go ahead.
Sourav?
Yes.
Okay. No, Benedict has his hand up.
Okay, since you already had a question, can you go back to the definition of the AZF, where A is an algebra? What, how was that precisely defined?
Yes.
Okay, so it's not defined. It's not clear to me that this is even axiomatizable.
Yeah. Okay. But the thing is that, yeah.
I mean, maybe this is not bad, but because I mean, you are quantifying over all possible models of set theory, and then you're building all of these V of A's, and you take the intersection of all of those.
Yes.
A terrible thing.
Yes, of course, true. But the point is that actually this gives much more deeper questions, like what happens like if we take only the Boolean algebras, like this A and B, all are Boolean algebras, make these cross products and make the intersection.
Mm-hmm.
Like that means that the theory we are getting, we don't know whether it is axiomatizable or not. But the thing is that whether it becomes classical.
Yeah,
If not,
I didn't really mean this as criticism or anything. Just an observation that as opposed to the other theories where we give them by axioms, in this case we give this by essentially a meta-mathematical definition.
Yes, exactly. That's true. That's true. Yes, of course, true. Yes. Yeah, actually the point is that we are working on this thing, like few questions we have in our mind, like these are actually related to the classical one as well. Like, is this a case that if whenever we talk about something independent, we, like, other than the, like, is it possible that to say some formula is independent from the classical set theory, but we cannot prove it by the Boolean valued model construction? Is it possible?
If you fix one algebra, and in particular your finite ones, it would be rather surprising if it wasn't axiomatizable, right? I mean, if you take A to be the 3-element Heyting algebra, I think I would be amazed if this turns out not to be axiomatizable at all.
Yeah, no, probably for some cases it will be axiomatizable, but we don't know about all the algebras A. But the point is, what I'm saying, that like we don't know, like it is actually leading us to that point. Like, is this a case that whenever we are talking about independence of some formula, is it true that always we can find two Boolean valued models where one makes that formula true and another one doesn't make it valid? Like, it is actually taking us to that point. Like how much strong the Boolean valued model constructions are to prove the independence of the sentences. We don't know. Like, and this is actually leading us to that point.
Mm. I mean, the dependency on the choice of V is something that your theorem about GCH, of course, shows.
Yes.
So I mean, the theorem about GCH says that the truth value of GCH in the model V is retained by the algebra valued model, and therefore, if you take different V's, you don't get the same theory.
Yes, exactly. That's true. Yes. Yeah. But the thing is that whenever we are defining here, we are taking we are fixing V. We are not changing it in this definition. Like, we did not say anything about the V, but just we are taking the actual universe of set theory. That's all. We are fixing V. We are not saying anything about V.
That's not how I understand the definition, because the definition says it's said in all algebra valued models of the form, which I think is a hidden quantifier saying for any model of set theory, any model of ZF V.
Actually not. Like, here we are fixing V. Like,
but then it's clearly not. And it's clearly not axiomatizable, because then it's just a complete theory, right? Because then it's just the theory of that V of A.
It's not actually of V of A. It is something, a proper fragment of V of A.
Yeah. But yeah, okay, but still, I mean, then, no, but I don't think you mean that. I don't, because otherwise V should be in the notation, right? Otherwise it should not be called AZF, it should be called A, VZF.
Yes, so yeah, you are right, like that we should, in writing of this notation, this parameter V should be somewhere here inside. But as we have just written in the paper, like we have just mentioned that this V is, we are fixing this V, and then all the other things we are just stating.
Giorgio has switched on his camera. I think he wants to say something.
Yes.
Hi, everybody. Yes, and thanks, Sourav, for the talk.
Thank you.
Benedict, for the question. Just a very small point in clarification. I mean, Sourav didn't get into the details of this product construction, but the validity in the product construction is given by the fact that something is valid in both algebra valid construction, V of A and V of B. So as long as we're allowing the B to be any Boolean algebra, the theory is not complete, exactly because we are losing every sentence that is independent. So because changing the B, we change actually the possibility of having something that is valid in V A cross B. So we're actually shrinking a lot the sentences that are actually valid in this AZF. But I mean, there's a lot of details that Sourav didn't get into, yes. And these are very strange models. But I agree with you.
Want to fix V.
But yes, we fix a V. Yes, there is in this notation it's not clear, but there is dependency on V, and it should be yes.
For example, if you start with a model V that is a model of ZF is consistent, or a non-standard model where ZF is inconsistent, you would expect to get very, very different sets of axioms in there, right?
Yes, yes, that's true.
But the general idea was to avoid the problem to fix V to be the real V, whatever this means.
I don't understand that.
But yes, I mean, there's a hidden variable, and yes, strange things can happen, and we get different theories. Yeah.
Yes.
And may not be axiomatizable.
Mm.
Yes, that's true also.
But so what I was suggesting, apparently not what you had in mind, but just taking the intersection over all models of ZF, yes. Which would be a bit more like I mean, that has a much better chance to be axiomatizable, because it actually is the axioms of ZF then that you're talking about.
Probably yes, and we have to think about it in future. Like probably yes, like start with the intersection of all the models as V, and then see that what kind of thing we can find from that V across B. Yeah.
Yes. No, I agree completely. Yes, that would be, but that was not the focus of this of the work. I mean, to define these theories, but just to say that the independence theorem actually is a schema of independence theorems that can be applied to any theory that is actually fragments of CFC. So we weren't really interested in the specific theory, but you're right. I mean, if we take the intersection of all the V's, then it might get axiomatizable.
Yes.
Yeah, I think Jan had some question. Jan wanted to ask some question.
Well, it's not anything very deep and technical here. I mean, it was a more innocuous question. I wanted to ask, what are the kind of main techniques in proving these theorems? Is forcing the essential idea, or is it?
Okay, so another interesting point, like. No, actually, we could not develop the idea of forcing till now, but our work is going on in that direction. Actually, there was some problem in developing forcing in all these kind of constructions. And for that problem, like again, if I just want to say that which kind of problem it was, like it will again take some time, like we don't have that probably. But what I can say that actually we have overcome that problem, and we are very much what to say, like hopefully we can develop some theory of forcing in non-classical set theory, which actually we are working with already, Giorgio, me, and Santiago. The point is that how we have overcome that problem just by changing the interpretation of equality algebraically. That means that if you go to the beginning, and if you just take these two things here, you see that the belongingness and equality are defined like that, and then we are doing all other things, right? But then what we did in our new construction, like what we are working with already, we have changed this equality. And by changing this equality such a way that which actually remains equivalent in the classical case with this one. And we have overcome the problem which was restricting us to get the theory of forcing. Like, no, I should not say the theory of forcing is a big thing, but at least to get entered to the theory of forcing, the main restriction is now deleted by changing the interpretation of equality in some other way, which is actually equivalent to this one in classical case.
Thank you.
Yeah.
So, any other question or comment? If not, then let us thank the speaker once again for this wonderful talk. And
Thank
with
you.
this, we end today's second lecture. Thanks to all the participants for giving their valuable time to attend this event and to make it successful. Thanks to all. So I think we can now disconnect it. Thank you.
Thank you. Bye-bye.
Bye.
Bye.